Okay, I think I could. So first of all, some definitions, some notations. I will work with this P alpha. P alpha is power mean. It is generalization of arithmetic mean. All of you know arithmetic mean. We add the alpha's powers of xi, some real numbers, non-negative real numbers, divide them by n and raise to the power 1 over alpha. Of course, one should clarify what this means when alpha is 0. When alpha is 0, then we assume that this P alpha is the geometric mean of these numbers. If alpha is negative, there is a problem with zeros in the denominator, because if alpha is negative, then xi will be in the denominator. And in those cases, we assume that if xi are 0, then one of the xi is equal to 0, at least one of them, and alpha is negative, then we assume that P alpha is just 0. So we are done with clarification of these exceptional cases. Power mean is defined for all non-negative real numbers. This definition is given in Hardy Littlewood Polya's well-known book Inequalities. So it is well known that as alpha increases, power mean increases. This gives the following sequence of inequalities. So for P minus 1, when alpha is minus 1, you get harmonic mean, which is less than P0, which is geometric mean, which is less than or equal to P1, which is arithmetic mean, which is less than P2, which is quadratic. Well-known inequalities. One can see the implications of this inequality and some applications in encyclopedic books by Beckenbach, Bellman, Bullen, Mitrinovich, and there are many other books about inequalities. So the applications of these inequalities go beyond mathematics. There are many applications in physics, engineering, and other scholarly fields. So I'm interested with the following question. I want to know how large or how small can AN minus GN divided by P alpha minus GN be for all possible choices of alpha. So I'm trying to find maximum and minimum if there are any of this ratio. For n equals 2, this was done by many mathematicians in many different papers, some of which were not aware about the earlier works. So I found these references, probably there are many others. So by Wu in 2011, by Omran Kuba, Syrian mathematician, in 2014 by Jameson, recently in 2023. For n equals 2, this was done by many mathematicians. I'm trying to do this for other n, for n greater than 2. There are also works in this direction. So for n greater than 2, some intervals of values for alpha were studied by Wu and by Wen and his co-authors, which you can see here. These works considered only some special cases for alpha, not all possible alpha. So this study will complete these works and give full picture of what can happen for different values of alpha. There are this kind of questions were studied for other means by many mathematicians. For example, this one on a recent work from 2022 by Din, Dong, and Nguyen in Indian Journal of Pure and Applied Mathematics. They considered the problem for weighted means, only special case of the problem. I found many other papers in which similar problems were solved for other means, harmonic mean, quadratic mean, and other exotic means such as the first and second Seifert means, the identic mean, the Neumann-Sandor mean, Sandor-Young mean, the logarithmic mean, the contraharmonic mean, the bivariate mean, Sandor means x and y, etc. There are many other means, but in all of these works, only the case n equals 2 was considered. So the problem becomes harder as n increases, of course. So in a certain sense, the work that I present today will be first work in which all cases were considered for one choice of mean. By all cases, I mean all possible values of alpha. Before starting the discussion of the results, I want to mention some applications. These applications were not considered by me. I saw them in the papers that I have shown you. So there are some applications in entropy transport problems. It can be seen in the paper by De Ponti. There are applications in geometry, Euler and Finsler-Hadwiger type inequalities. There are applications involving Ali type inequalities, about which you can read in the paper by Woodstange. There are also applications for inequalities involving the power of eigenvalues of Hermitian matrices and integral mean involving permanent complex matrices, about which one can read in the paper by Wen, Cheng, and Gao. So there are many interesting applications of the inequalities that we discuss, but I'm mainly interested in mathematical part, and I will present only mathematical part. There can be many other applications. First of all, I will need some lemmas. This one is elementary lemma. It says if alpha, beta, gamma are delta, and delta are real numbers, and gamma is not delta, then the difference of power means corresponding to these parameters when x1, x2, xn approach to xx dot x. So when all of the numbers approach to one and same number, then this is equal to alpha minus beta divided by gamma minus delta. This is an exercise in calculus. I included it in the paper with its proof. I also needed a second lemma. It is crucial lemma in my study. So if x, y, and z are positive numbers, r is different from 0 and 1, and x is less than or equal to y less than or equal to z, x, y, z is fixed equals to alpha, x plus y plus z is fixed equal to beta. Alpha and beta are positive constants such that beta cubed plus is greater than 27 alpha. This is to make sure that such numbers exist. Then as y increases, this sum of r powers decreases when r is greater than 1 and increases when r is less than 0 or r between 0 and 1. So if r is greater than 1, then the maximum and minimum of function hxy, this function, are achieved when x is equal to y less than z and x is less than y equals z respectively. If r is less than 0 or r is between 0 and 1, then the maximum and minimum of function h, x, y, z are achieved when this happens, this two. So the opposite. So why do we need this lemma? So in power mean, we have sums of this type, but many variables. Here I take only 3 of them. As you can see, sum is fixed, product is fixed. So when I change x, y, z, I don't change anything in geometric mean because product is constant. I don't change anything in arithmetic mean because that one is also constant. The only changing thing here is power mean. And in the power mean, I change only 3 of them. I chose x, y, and z. There are n variables, x1, x2, xn. I choose only 3 of them and denote them by x, y, z. And I can maximize this, minimize this without changing arithmetic mean and geometric. This idea will be crucial. So I proved this lemma. I can explain this also on the picture. This red one represents the surface xyz equals alpha. This blue one, not blue, green one represents plane x plus y plus z equals beta constant. So their intersection is a curve, which is blue. And since I restrict to the case x less than or equal to y less than or equal to z, I have to look only at this part of the curve. And then I prove that on this curve, x to the r plus y to the r plus z to the r is monotonic on this curve. So it is maximal at one endpoint, minimal at the other endpoint. Okay. I will return to this idea later, but this is crucial lemma in my results. I also use this lemma from Hardy-Littlewood Polya. It is very interesting lemma. Many works use this kind of results in their study of maximum minimum problems. So if f1, f2, and f1 prime divided by f2 prime are positive, increasing functions, then f1 over f2 either increases for all x in this question, or decreases for all such x, or decreases to a minimum and then increases. There is a very elementary proof of this in Hardy-Littlewood Polya's book on page 106. Particular case is also important, interesting. If f10 is equal to f20 equals 0 in this lemma, then f1 divided by f2 increases for x greater than 0. Some variants of this lemma were frequently mentioned in literature. So this version is just a special case. It is given in Anderson, Vamanamurthy, and Vurinen's book, Conformal Invariance Inequalities and Quasi-Conformal Maps. So it says that under the conditions that we already mentioned, if f1 prime divided by f2 prime is increasing on interval AB, so are these ratios. If this ratio f1 prime divided by f2 prime is strictly monotone, then the monotonity in the conclusion is also strict. This is a special case of Hardy-Littlewood Polya's in lemma, but it is very useful. Okay, so in the following, we will focus on the study of maximum and minimum values of this AN minus GN divided by P alpha minus GN. Of course, this question is meaningful if alpha is different from 0 and 1. because if alpha is 0, then P alpha is just geometric mean, so the denominator becomes 0. If alpha is 1, then P alpha is just AN, and therefore you obtain constant value 1. So we will assume that alpha is 1 over R, and R is different from 0 and 1. Sometimes instead of P, we will just write, instead of P alpha, we will just write. Also note that without loss of generality, because this expression is homogeneous, we can assume that the sum of the numbers is 1. Because otherwise, if it is not 1, we can just divide all the numbers by their sum. And this will not change anything in this expression, because numerator and denominator are just multiplied by the same number, and therefore they cancel each other. So the sum is 1. Case n equals 2, as it was mentioned before, is well known, considered as many papers. So in our paper, in our study, we will assume that n is greater than 2. Since, as we already mentioned, we have to look, since we are interested in the maximum minimum values, we have to look only to the case when n minus 1 of the numbers x1, x2, xn, n minus 1 of them is equal to x, and the remaining last one is equal to 1 minus x. If you remember in this lemma, we proved that maximum minimum can occur only when out of 3 numbers, 2 are equal to each other. So there are n numbers, x1, x2, xn. For any 3 of them, 2 of them should be equal to each other. This means that we can assume that n minus 1 of the numbers is equal to x, and the remaining number is equal to 1 minus x. So we can assume this automatically. Our problem is reduced to one variable problem. Of course, there are technical details of the proof that I skipped. So a very hard problem about n variables became just one variable problem because of that lemma. But still, it is still very difficult to study this function. Even though it is one variable function, it is not trivial to find its maximum minimum values. Again, I skip technical details in the proof and go directly to main results. So this theorem gives all possible cases. This is first result of this type in the literature. So if alpha is negative, by the way, alpha is negative was never studied before. If alpha is less than 0, then this ratio is not bounded from below, but from above it is bounded by some number, which is determined by that fx. I also have some approximations about this maximum. If alpha is greater than 1, then it is bounded from above by this exact number, from below by some minimum. If alpha is between 1 over 2 and 1, and n is less than 1 over 1 minus alpha, then our ratio is between 2 numbers, one of which is exact, the other one should be determined using fx. If alpha is greater than or equal to 1 over 2 but less than 1, and n is greater than or equal to 1 over 1 minus alpha, or if alpha is between 0 and 1 over 2 included, and n is greater than or equal to 1 over alpha, then an minus gn divided by p alpha minus gn is between these two bounds. So this type, this variant appeared in the literature. So this variant, one of them appeared, not both of them, one of them appeared in the literature. So this result contains the previous results of similar type. And the last case, when alpha is between 0 and 1 over 2, and n is less than 1 over alpha, then again ratio is between two numbers, one of which is exact, the other one is determined using fx. The proof is very technical. And let's say I put it in the archive. One can read the paper there. Instead of the technical details, I want to mention some implications of this. So the obtained results can also be interpreted as the best constant inequalities, generalizing arithmetic mean, geometric mean inequality. For example, part 4 of theorem above, part 4 here, can be interpreted as the following inequality. AN is greater than or equal to this combination of power mean and geometric mean, less than or equal to this combination of power mean and geometric. It is natural to ask, what are the best constants for this inequality? So for the left inequality, the best constant for delta is this, and for the right side, the best constant is this. So what we found in our paper, can be interpreted as best constant inequalities. So one can say these inequalities are sublinear and superlinear bounds for the arithmetic mean in terms of the power mean and the geometry. One more note, comment. If all xi are replaced by xi to the 1 over alpha, so in the arithmetic mean, geometric mean, and power mean, if I replace all xi by xi to the 1 over alpha, then automatically the inequalities are transformed to this type of inequalities, which are frequently mentioned and discussed in other papers. So power of power mean, arithmetic mean, and geometric. R represents 1 over alpha. I skipped the proof, which is very detailed. So instead, I want to show you some applications. So the first application is this inequality. So one can give a new proof for this inequality, which was proved in 2005 in the paper by Wu, Journal of Meta-Analysis and Applications. Wu refers to a problem, open problem by Janusz in problem solving journal Crux Mathematicorum. And it was discussed there and conjectured that probably this inequality is true. It was proved by Wu in 2005 after 15 years of its publication. So you probably already noticed the similarity between this problem and our problem. So here it is power mean, but raised to nth power because that 1 over n disappeared. This is geometric mean, also raised to the nth power. That's why radical disappeared. This is arithmetic mean raised to nth power. So the problem is similar to this last one that I mentioned here. And using the results of the paper, of my paper, one can give a different proof, new proof for this result. Another application is this very old result. So it is about symmetric polynomials. You know symmetric polynomials. S1 is just sum of the numbers. S2 is the sum of the pairwise multiplication. Sn minus 1 is the sum of all products, each of which misses one x1, xi. And Sn is the product of all of them. So these are symmetric polynomials. There are many interesting inequalities about symmetric polynomials. One recent paper by Terence Tao proved this type of inequality. I think it is not yet published. It is just in archive for now. He also cites this paper by Sato in Crux Mathematicorum. So Sato proves this interesting inequality that f, which is written here, is between 0 and 1. Very sharp inequality, very interesting inequality. The form is very interesting. 1 minus 4s2 plus 9s3. In general, minus 1 to the n minus 1, n squared sn. This is always between 0 and 1. Now, in view of the results of the current paper, I can give a completely different proof for this inequality, completely different approach to this inequality. I think I'm done. These are all the results that I wanted to share with you. Thank you.